Okay, hi everybody. So now we're on our last and final section of our calc class. So this is the last section that's actually going to be on your exam. And in this section, we're going to talk about areas between curves. So what exactly does that mean? So previously when we were doing integrals, we knew that we wanted to find the area under a curve between two bounds A and B. So before, all we had was a simple curve like this, and we had a value A and a value B, and we found the area between that. And we said, in order to do that, we need to integrate this function. We need to integrate this function and evaluate it at these bounds. But now, how exactly do we find the area if we have two functions and we want to find the area between them? So for example, say we had this scenario going on here where we had some function g of x and some function f of x and g of x, and we want to find the area between them. So that means that we are trying to actually find the area between them. So we're looking for this area here. How exactly do we do that? Now, before when we had integration, we learned that in order to actually find the area, we did what's called Riemann sums. So we created little triangles here and made them infinitely small in order to find the area, where each of the widths were d of x or delta x, which said that we're taking delta x to be really, really small and had a lot of them. And that's how we approximated the area. So in order to approximate the area between two curves, we're kind of going to have the same idea. So what we're going to want to do is, for example, if we were to create those rectangles again, I mean, we're not going to be evaluating these with Riemann sums, but just to give you the idea how we're going to go about this is, if we were to create little triangles here, rectangles here, right? And we were to make them infinitely small, the width of each of these rectangles right here, this width here would be our delta x or our dx. Okay, and now we have to consider, now what's the height of the triangle? I keep saying triangle. What's the height of the rectangle? So what's this height here? Because before, the reason that we had to do, we integrated with respect to whatever we integrated this function was because the height of the rectangle depended on how high we were in the function. Well, here, that's not necessarily the case because we have a bottom function we have to account for and a top function. So the height of this rectangle here is going to be the difference from the point of this function g of x and this function f of x. So the difference between these two is going to give us that distance between them. So the height of this rectangle is the top function minus the bottom function. So in this case, it's basically just our f of x function minus our g of x function. And that's the idea that we're going to have when we are trying to find the area between those two curves. So in essence, what I want you to remember is that the area between two curves is equal to the integral from some bound A and some bound B from the difference from the top function minus the bottom function times dx, so times the width of the rectangle. So this is basically going to give us our height, and this is going to give us our width. So in that way, we get infinitely small rectangles. Now, this is the case for rectangles who are vertical. So the rectangles we drew here are verticals, and so far we've only really dealt with vertical rectangles. So I'm gonna go ahead and give you that formal definition for the vertical slices, is what I'm gonna call it. And then instead of doing examples on this right now, I'm gonna actually introduce another way that we can also have rectangles, and then we'll have a video separately just with examples. Okay, so that formal definition of the area between two curves with vertical slices, and again, we're talking about the vertical slices as in the slices of that rectangle that we're cutting. So how we're cutting these rectangles, how we're approximating. Okay, so if we consider a region bounded by the curves y equals f of x and y equals g of x, just like we have here, and x equals a and x equals b, so we're talking about the bounds where we're cutting it. And of course, f and g have to be continuous so that we can be able to integrate it. And our f of x is greater than g of x for all x in a, b, then the area of the region is going to be f of x minus g of x times dx, which is really just top minus bottom times dx. Okay, and the reason I kind of want you to keep this always in the back of your mind is because what happens if g of x is greater than or equal to f of x, so that means that g of x is the function that's on top, and f of x is the function that's on bottom, then your area in this case is still going to be the integral from a to b, but now you're going to do g of x minus f of x dx. And I'll show you exactly how to do that, but just remember that your top function minus your bottom function is going to give you that distance of each of those rectangles. Okay, and so also want to point out that for these examples that I have here, I made bounds a and b. But let's say that you have a function. Let's see. This is just a thought. We'll do examples to really lock this in, but let's say you have a function, two functions that they don't give you those values a and b. They give you that this is f of x, and they give you that this is g of x. Oops. Yeah, this is g of x, and they want you to find this area between the two curves. Now, how would you do that? So in order to be able to do this, what you're going to need to do is you're going to need to find where these functions intersect. So just keep this in your back of your mind and think about how exactly are we going to find where they intersect. We'll do examples like this, but this is something to consider. They might not always give you your a and b bounds, but you can definitely find them by finding the points where they intersect. Okay, so now let's do the horizontal slices. Okay, so for the horizontal slices, what I want you to consider is what happens if we have some graph where it doesn't exactly look like this, where f of x is like this and then g of x is right underneath it, or vice versa. So what happens if you have a function that looks like, let's say we have a function f that looks like this, and a function g of x that looks like this. I don't know, I'm just making these things up. And let's say now they give you your bounds are no longer in terms of x. They want you to, your bounds are no longer x values, your bounds are now y values. So what I mean by that is, what if they give you that y here is equal to c, and then here y is equal to d. And they want you to find the area between these two curves bounded by d and c, which means they want you to find the area here. How exactly do we do that? Well, first of all, notice that our bounds are with respect to y. So things got a little flip-flopped. Here we had a and b, and those were x equals a, x equals b. Here we have y equals d, y equals c. So that means something weird is kind of happening. This means that our function, our independent variable, has now become y, and our dependent variable is now x. So this means that our function here is actually f of y, and our function here is g of y. And you'll be able to see that in the problem. Again, we'll do examples to really lock this in. Now, if we consider how we applied Riemann sums in order to approximate that area, and we wanted to use rectangles in order to do that, it really wouldn't make sense to draw our rectangles this way because our lower bound here is always going to be C, and our height is always going to be D for these, but then when we start to get to here, we can't really approximate what's going on there. It doesn't make sense. So in this case, we'll be drawing our rectangles. Let me do a different color so you can see it a little bit better. Black is good. So that our rectangles actually are of this shape over here, like this. So our rectangles here would be horizontal because now this spot here depends on f of y, and this spot here is going to depend on g of y. So we have that dependence. And now the width of this here is going to be a small change in y. So remember that a small change in y, we can also write that as dy, which is the same thing as delta y in this case. So I want you to consider a small change in y, and we're going to refer to that as dy. And then again, now if we wanted to find the distance between this point here and this point here, how do we do that? Well, before in the last example, we had that the distance was our top function minus our bottom function. But in this case, we don't have a top function and we don't have a bottom function. But we do have a left function and we have a right function. So to find the distance between them, so that width or that height here is going to be the right function minus our left function. So this means that here we're going to be doing f of y minus g of y. So when you have horizontal slices, your area, what I want you to remember, is going to be the integral from c to d from our right function minus our left function times dy. And of course, I'm still going to give you that formal definition, but it's good to remember in terms of right minus left dy, so that when you see a picture, you can automatically see what's going on. Okay, so now let's do that formal definition. Okay, perfect. So in this case, like I mentioned, we have horizontal slices and not vertical slices. So things tend to change a little bit for this. So if we have a region, just like the one on top, bounded by f of y and g of y, and c and d, where y equals c and y equals d, and again, f and g do have to be continuous, and f of y does have to be greater than g of y for all y, then the area of this region is going to be defined by this, which is really just the right minus the left times the width. Okay, and like I said, this part is important. If they give you the reverse of this, if g of y is now bigger than f of y, then you're going to flip your area accordingly, so that it's g of y and minus f of y times dy. And again, they don't always necessarily have to give you these bounds. Sometimes we have to find out where they intersect. And we'll do a couple of examples. But before we do that, I'm going to actually talk about how we are going to approach these problems. So I'm going to give you some steps for these, or some like guidance before we go ahead and jump into some examples. Okay, so this is the lot, but this is just kind of, and maybe you just want to write some shorter bullet points, but this is the general approach. So the first thing that you want to do is you need to find your region. So what region are you looking at? So what do we mean by that? Well, if we look back here, here the region we were looking to find the area of was this yellow region, just like here. if they do give you that region, you have to find out, did they give you an A value? Did they give you a B value? And if they don't have those A and B values, then you need to find where those intersect. So you may need to find where the curves intersect. And in order to do that, you'll set the curves equal to each other. So here, in order to do that, you'll do, for example, find out where f of x is equal to g of x, because that's going to tell you where they intersect, or where f of y is equal to g of y in the horizontal case. And now you're going to determine whether they're going to be sliced horizontally. And if they are sliced horizontally, you're going to integrate with respect to y. Then that's because now your widths are in terms of dy delta y. And so you're going to be integrating with respect to y. So you're always going to be integrating with whatever variable that rectangle is. And if it's a vertical slice, you'll be integrating with respect to x. Okay. And here again, I just kind of rewrote what we wrote earlier, is to slice vertically. Then you are going to do the top and subtract the function on the bottom. To slice horizontally, you will do right minus the left. And then you're going to integrate the difference of those functions and evaluate them at your new A and your B values, okay? And so I'm going to go ahead and stop this video here. This is just a general layout of what you're going to be doing this for this chapter. And we're actually done with the concepts of it. And in the next video, I'm just going to run through a bunch of examples so that you get used to all of this, okay? So this was just kind of the theory behind it, what we're going to be doing, and why we need to do, right and left. Next video is just going to be examples using these approaches of finding areas between two curves.